I will come to another defect for another type of stainless steel, say AISI 310S. I have mentioned to you that this particular grade is having austenitic solidification, like high carbon equivalent you have austenitic solidification, beyond say 0.5 you have only austenitic solidification. Similar is the case for A310S, for the nickel equivalent or chromium equivalent above 0.74. Between 0.55 and 0.74 you have peritectic range, above 0.74 you have totally austenitic solidification. That means you have initially liquid, then liquid plus austenite, and finally austenite when it is solidified, no other transformation. So, what is the peculiarity for such grades? I have mentioned, since this is austenitic solidification, incidence of microsegregation is quite high. I have given you the figures earlier that between delta solidification and austenitic solidification, incidence of microsegregation for austenitic solidification is relatively high for the deleterious elements like phosphorus and sulfur. I have given you figures earlier. For austenitic solidification it is relatively less, this values of K. Values less means you have more segregation. So, if you have more segregation, what is the problem? Problem is twofold. First, the interdensity regions are more rich in all these elements, phosphorus, sulfur and other allying elements. That is number one. So, the interdendritic areas are relatively weak because it is too much of segregation, number one. Number two, because segregation is more, the solidus completion temperature, that means the final solidus temperature, actual solidus temperature when the solidification is complete, is also depressed or it is coming down. So, mushy zone is increasing. So, during solidification the shell thickness, solid shell thickness is less and the mushy zone is quite deep and wide. So, what is the implication of that? Implication is there can be lot of sticking tendency, there can be lot of because of this the shell is thin, that means shell cannot withstand the pressure, whatever pressure will be generated due to due to maybe ferrostatic pressure or due to mechanical strain, whatever is there. So, there will be lot of possibility of formation of cracks, intercolumnar cracks in slab. These intercolumnar cracks in slab, when you are finally intercolumnar cracks means these are internal cracks. You may not always see them on the surface, but these internal cracks, I have told you, slabs may have a lot of internal cracks because of weak intercolumnar areas. This is particularly true for high nickel equivalent by chromium equivalent situation, a grade like 310S or a chemistry like more than 0.5% carbon, where it is a totally austenitic solidification. The shell is very thin during solidification. So, the chance of lot of crack formation in the shell, because it is thin, it is relatively weak. So, these intercolumnar cracks in the intercolumnar regions, finally when you are rolling the slab they will come to the surface and you get surface tears, we call it, in the hot rolled plate or slab. So, these 310 slabs have been rolled to plates and it has been found that there are a lot of surface tears, that means surface cracks, maybe fine or maybe slightly deep cracks, slightly longer cracks. So, these are basically originating from the internal intercolumnar cracks in slab, which are existing in slab subsurface or at the interior of the slabs, internal locations of the slab, which are coming to the surface during hot rolling. So, what has to be done? As I have mentioned, this is basically happening due to microsegregation, so austenitic solidification. So, the solution lies in controlling the amount of phosphorus and sulfur. That is what we have done. So, you see, when the phosphorus and sulfur content is relatively more, so 0.6, the incidence of such defect is very high, say about 40%, 35%, 40%. And if you can bring this phosphorus or sulfur to as low as 0.3, you see the incidence has come down to less than 10%. So, depending on what is the type of defect, what is the alloy, the solution has to be accordingly decided. In 304 depression type of grade, we adjusted the chemistry by controlling nickel equivalent by chromium equivalent, bringing down it from slightly higher than 0.55 to less than 0.55, and we got much improvement in as far as the incidence of depression is concerned. For 310S, it is austenitic solidification, different from 304, totally different sequence of solidification. Here the problem is intercolumnar cracks which are located internally in the slab. 304 more problem was surface depression, and because of the surface depression there was subsurface cracks. Here the problem was internal cracks at intercolumnar locations in slab. They are giving rise to or resulting in surface tears in the hot roll plate, whatever has been done from the slabs. So here since it is a totally austenitic solidification, you have to control or rather reduce the intensity of the defect by controlling phosphorus and sulfur, which are notorious elements as far as segregation is concerned, microsegregation is concerned. So the solution lies in controlling the phosphorus sulfur. So the control of phosphorus and sulfur is more important for austenitic type of solidification as compared to ferritic type of solidification. In ferritic type of solidification, this much of control would not have resulted in much improvement except very minor improvement, but here it has a dramatic improvement. So again I am repeating, depending on what is the type of solidification, what is the type of grade, you have to decide what is the solution. A typical alloy, a typical grade will have a particular defect. All defects are not identical, whether it will be a surface defect, whether it will be an internal defect, it may depend on the solidification sequence, it may depend on the chemistry. As I have mentioned several times, the so called peritectic grades, it has a particular type of defect. Defects are more at the surface for such type of grades, more of depression that is on the surface. Because of the depression there may be subsurface cracks, but the problem is depression, problem is surface cracks. So if you can control those, if you can have a better surface, we are successful in having a good quality. But for 310S, problem is something else, problem is more of internal cracks. So what you have to do? You have to control phosphorus and sulfur. Sulfur you can control somewhat, again I have to telling you, by using a higher ratio of manganese by sulfur, more than 25, more than 30 say. But for phosphorus there is no other element which can take care of. So you have to control phosphorus to get a better quality steel where this type of cracks, the incidence of this type of cracks are relatively less. So I have mentioned to you different type of defects. First I have mentioned about the defect at the central region. It can happen in all types of grades, but it will be relatively more for austenitic grades which are undergoing austenitic solidification. Why? Because their microsegregation is relatively more. Because microsegregation is more, the segregating elements will get a chance to segregate towards the last stage of solidification. So these defects are relatively more in slightly higher carbon chemistry which is having higher carbon, or in stainless steel which are having higher nickel equivalent by chromium equivalent. So what has to be done there? You have to use mechanical soft reduction to control the central defect. Mechanical soft reduction I have mentioned, two things are very important: where you use the mechanical soft reduction, at what location, and what is the intensity of the soft reduction. How much pressure do you put, how much thickness you reduce so that creates the pressure. I have mentioned the two things are important: where you put mechanical soft reduction and how much of intensity of soft reaction you are giving. If you put relatively less amount of pressure, it may not be adequate, it may be inadequate to compensate the shrinkage, formation of shrinkage, central shrinkage. So, you have to have adequate amount of reaction, but if it is more than adequate, so it will create more harm than good, it will generate internal cracks. That is why for any factor there is an optimum range, nothing can go beyond that. So, it should not be too low, it should not be too high, it should be adequate within the desirable range. So, the location as well as the intensity, the amount of reduction is very important to get a good internal quality, where cracks will be less, almost nil, segregation amount will be less, and it will be distributed as I have shown in the figures. Here you see there is both crack as well as segregation at the central region, the intensity is quite high. Using mechanical soft reaction in the same alloy, same grade, same type of continuous casting parameter, same type of caster, only difference was we are using this facility, mechanical soft reduction in the caster. So, that means certain areas of the caster where solidification is getting completed, there we have given mechanical soft reduction by changing the distance between the rolls. Basically, how we are giving mechanical soft reduction? We are changing the distance, these are the rolls, So, we are changing the distance between the rolls. The normal distance is this, we are slightly decreasing the distance and finally coming to the desired distance. So, in this process we are putting some pressure, we are giving some mechanical reduction, but again I am telling it is called soft reduction. It is, there is a gradient, slowly it is increasing, not suddenly. If you suddenly increase the reduction, that means you will give some sudden strain which is not desirable. So, the strain rate is important, slowly it should increase, the value should be relatively less, the rate of increase should be low, the strain rate also is important, it should be relatively less. So, these are important issues which should be kept in mind. So, the central quality can be improved by mechanical soft reduction. Then the depression in 304 type of peritectic grades stainless steel, it can be improved by controlling minor adjustment of chemistry, by having the chemistry which is slightly less than the peritectic start, nickel equivalent of chromium by nickel equivalent divided by chromium equivalent value of 0.55 I have told you is the peritectic start chemistry. So, instead of slightly more than this, you should have a slightly less than this nickel equivalent chromium equivalent. So, then only you can avoid this delta to gamma during solidification. This delta to gamma transformation for this type of chemistry will be having lower than, at a temperature which is lower than the solidification complete temperature. So, that delta gamma transformation strain is not present in the crucial brittle temperature region which is around solid dust temperature. This is the strategy which we are following here. By minor adjustment of chemistry, delta to gamma transformation, we are bringing it down from around end of solid dust to lower than solid dust. If it is lower than the solid dust, the crucial brittle temperature range we are avoiding. The crucial brittle temperature range is between solid fraction of 0.9 and 1, between the temperature of liquid impenetrable temperature LIT and I have mentioned earlier it was 0 ductility temperature ZDT, which coincides with solidification completion temperature. So, if you can have the delta gamma transformation at a temperature lower than solidification completion temperature or ZDT temperature, then the problem is tackled to a large extent. So, this is the strategy we are adopting for 304 type of steel where you have lot of surface depression. Now another type of defect is the intercolumnar cracks, internal cracks in 310S type of stainless steel. Similar cracks will be there for ball bearing type of steel, which is a totally austenitic solidification. Similar type of crack we may have for a steel which is having 0.5 or 0.6% carbon. So there what strategy we have to follow? We have to control phosphorus, sulfur and increase the manganese by sulfur ratio, so that the extent of segregation is less. If the extent of segregation is less, the shell thickness will be relatively more and the interdendritic region will be relatively less impure because of lower, relatively less amount of phosphorus and sulfur. Segregation is less means segregating phosphorus, sulfur and other alloying elements will be going to the interdendritic area relatively to a lesser extent. So in that process you can control the intercolumnar cracks. So the solution lies in controlling phosphorus and sulfur. So again I am telling you, first you have to understand for any grade what is the type of solidification, whether it is sticking type characteristic or it has a depression characteristics. Accordingly you have to select the solution, you have to select the casting parameters, you have to select possibly the chemistry, optimum chemistry range, as I have mentioned for 304 type of grade. I can give some more examples, maybe later I will give you some more examples, but today I have mentioned 3 types of defects which can be tackled or brought down by having suitable strategy. 310S grade of steel, the problems are intercolumnar cracks in slab which result in surface tears, surface cracks for hot rolled plates, or even it can happen for the hot rolled, I am talking of plate here, it can happen for hot rolled coils also. So for this type of grade, solution is something. For a 304 type of steel, the solution is controlling minor adjustment of chemistry to bring it slightly lower than the nickel equivalent or chromium equivalent, slightly lower than the peritectic start chemistry, so that the delta 2 gamma does not take place within solidification range, it takes place lower than the solidification range and it avoids the so called high temperature brittle temperature zone between LIT and ZDT. So this is the technique which can be utilized. Another I have talked about how you can control the incidence of central segregation and central porosity. For this is maybe true for any type of grade, but it is the incidence are relatively more for sticker type of grades, for austenitic solidification grades where you have austenitic solidification and the mushy zone is relatively more. If the mushy zone is more, this problem is also relatively more. So you can control this by having soft reduction. I have mentioned here the location of soft reduction has to be properly selected towards the end of the solidification, final stage of solidification, and how much of soft reduction do you give, that is also important. If it is less than the adequate value, it will have no effect. If it is more than the adequate the optimum value, it may generate cracks. So the optimum level is very important. So again I am repeating, depending on the type of solidification characteristics, you may have different type of defects, whether surface or internal. Even in internal you can have at the center or at other locations. So if you understand what is the solidification sequence, then you can understand why those cracks are forming, what are the problems for those quality, why quality is getting affected. And if you understand that, you can devise the solution, you can devise the way which can take care of this problem. This is very important for understanding. Thank you very much.